A successful breach takes weeks of reconnaissance, but the moment the target machine reboots, the connection snaps. The attacker is locked out. Gaining an initial foothold on a network is strictly a temporary victory. To survive routine system interruptions, an adversary must establish a persistent backdoor. The traditional methods for maintaining this access, writing a new executable into an auto-start folder or scheduling a basic background task, generate massive amounts of forensic noise. Modern endpoint detection and response systems monitor the file system continuously. If a suspicious binary hits the disk, the EDR instantly flags the modification, quarantines the file, and severs the attacker's connection. To maintain long-term access, highly advanced threat actors stop fighting the operating system and start using it. They achieve extreme stealth by hiding within the native subsystems that Windows relies on every single day: COM object hijacking, WMI event consumers, and trusted process injection. By living off the land, these adversaries turn standard system operations into a self-sustaining backdoor that remains invisible to traditional file system monitors. The Windows Component Object Model, or COM, is a structural framework that allows different software applications to interact and share capabilities. To find these specific shared modules, applications query a class identifier, known as a CLSID. This is a unique alphanumeric string in the registry that acts as an exact address for a required piece of code. This flowchart illustrates the operating system's built-in search hierarchy. When a host application requests a CLSID, Windows first checks the current user hive, HKCU, before moving down to check the local machine hive, HKLM. This priority routing is intentional. Checking the current user hive first allows individuals to apply custom software configurations without altering the entire local machine for other users. An attacker operating with standard, unprivileged access exploits this exact hierarchy. They locate a legitimate CLSID in the local machine hive and duplicate it up into the current user hive. The OS will now stop its search at the user level. Inside that newly duplicated registry entry, the attacker changes the file path. Instead of routing to the legitimate Windows component, it points directly to an unauthorized malicious DLL. This creates an immediate operational risk for the attacker. The host application expects specific functions from that module. If the malicious DLL fails to return them, the application crashes and alerts the user. To maintain stability, attackers deploy an intermediate proxy tool between the application and the system. This proxy executes the malicious payload, but quietly forwards all the legitimate API requests back to the original local machine module. The host application receives exactly what it requested and continues running smoothly. The interception is entirely transparent. Because it relies on native Windows loading behaviors, standard security monitoring simply interprets the hijacked as a routine user preference configuration. Beneath the visible file system lies a deeply embedded engine, the WMI repository. Windows Management Instrumentation is the core administrative framework of the OS. It continuously queries system metrics, evaluates hardware states, and executes high-level management tasks. Attackers weaponize this engine by assembling these three specific interlocking components to form an autonomous execution chain. The first component is the event filter. This defines a specific trigger condition within the operating system, like a user logging in, a set amount of system uptime, or a sudden spike in CPU utilization. The second component is the event consumer. This dictates the exact action to execute when the filter is triggered. It is typically a hidden PowerShell script or command line instruction. The final component is the filter to consumer binding. This acts as the permanent registration link, securely fusing the trigger condition to the hidden payload. Once this construct is compiled into the repository, the attacker steps away. The moment the operating system naturally reaches the defined trigger state, the WMI framework automatically launches the concealed process. The execution originates directly from a universally trusted operating system service, giving the malicious activity the exact same privileges and appearance as a standard administrative task. The entire payload exists strictly as data compiled within the repository. Traditional antivirus scans searching the hard drive for malicious files find absolutely nothing because there is no file to find. By repurposing native management and diagnostic tools, attackers create a logic bomb that resides entirely outside the scope of traditional file-based defenses. When adversaries acquire administrator or system-level access on a public-facing network server, they can embed their persistence directly into the flow of enterprise web traffic. They achieve this by exploiting native HTTP modules within Internet Information Services, or IIS. This diagram shows the pipeline of the IIS worker process. The architecture is modular, allowing administrators to register custom C++ DLLs to inspect and process incoming web traffic before it reaches the main application. An attacker injects a malicious native module and positions it at the very front of the worker process pipeline. It now intercepts every single incoming data packet. To interact with this module, the attacker sends a standard HTTP request to the web server, but embeds a highly specific hidden custom header containing a command. The malicious module scans the incoming traffic. When it detects that exact custom header, it pulls the packet from the flow and immediately forks a hidden command line process to execute the instruction. The module then captures the output of that command and funnels it back to the attacker through the standard HTTP response stream. The packet is handled before it ever reaches the core web application. The application is entirely unaware of the transaction, meaning the malicious activity never appears in the standard web logs. By hooking deeply into public-facing services, attackers construct a continuous command and control channel that perfectly mimics legitimate enterprise web traffic. These advanced persistence mechanisms succeed because they do not break the rules of the operating system. They rely on the operating system doing exactly what it was engineered to do. Defending against these vectors requires moving beyond simple file scanning. Security teams must implement continuous architectural baselining to understand what normal looks like on their networks. For COM hijacking, defenders must actively hunt through the registry to identify anomalous, overlapping class identifiers that exist simultaneously in both the local machine and current user hives. To uncover WMI logic bombs, security teams must directly query the repository. Running this precise command audits the event consumers to expose unauthorized logic bindings. For application-level hooks like IIS backdoors, organizations need to continuously validate module load paths and monitor specific system event IDs for unverified module registrations. When the native architecture of the operating system becomes the primary threat vector, establishing deep systemic visibility is the only viable defense.